One of the main things that brings so many people to the San Francisco Bay Area is the land. It's a bold and rough-looking landscape, a land rich in sharp lines, sweeping curves, and striking contrasts. Nature works with a lively and powerful hand here, but it takes its time as well. These cliffs have been rising from the ocean floor for many thousands of years. More than 6 million people call the San Francisco Bay Area their home. And millions of tourists journey here every year for an unforgettable vacation. Almost everyone who spends time in the Bay Area is moved by the landscape. Ironically, most people also fear the dominant force that shapes this bold terrain: earthquakes. The Bay Area is dissected by one of the most active parts of the Earth's crust, the San Andreas Fault. On October 17, 1989, a section of that fault came alive deep beneath this remote mountain peak in the Santa Cruz Mountains. And for the first time, the world witnessed a major earthquake live and in color on their TV screens.
Zoom into Candlestick Park. For the first time in 27 years, a World Series game will be played in Candlestick Park. The Battle of the Bay continues. Game 3 of the 1989 World Series, the Oakland Athletics against the San Francisco Giants.
Flash forward to the bottom of the 4th inning. Dave Parker barely, by inches, just misses a home run. Candy Maldonado with the hesitation, allowing Jose Canseco to score, and he fails.
After a few brief minutes of downtime, television coverage of the World Series was restored, but baseball cheer had already faded.
I'm at the corner of Jefferson and Divisadero. You can see this building is collapsed.
Television crews quickly found the hardest hit areas around the bay, and live coverage of the unfolding disaster continued uninterrupted throughout the night.
Here comes the footage of the Bay Bridge. We showed it earlier. There is the cantilever section, and there, right at the end of the cantilever, is where the roadway dropped onto the lower deck.
The Loma Prieta earthquake was a major quake. At 7.1 on the Richter scale, it was the largest earthquake to strike Northern California since the great 1906 San Francisco earthquake.
The downtown section of Santa Cruz is basically gone. All the old brick, unreinforced buildings have collapsed.
Damage was severe near the epicenter of the Loma Prieta quake, which was located 10 miles east of the seaside city of Santa Cruz. But damage and loss of life was greatest in or near beloved San Francisco. We'll never forget the roaring fire in the Marina District or the ghastly scenes of the Pancake Interstate 880 viaduct in Oakland. We should also remember that these tragic events took place more than 60 miles away from the quake's epicenter.
Property damage during the Loma Prieta earthquake totaled as much as $6 billion. And yet this very high amount of damage was not widespread. It occurred in a few small regions. First, there was the region right around the earthquake where the shaking was most intense. But the most expensive property damage of all occurred as much as 60 miles away. Places like the Marina in San Francisco, where the ground was what we might call weak. It's well known that there are certain types of weak ground that can increase the ground shaking and increase the amount of damage that we get from earthquakes.
Ground shaking is the universal geologic effect of all earthquakes. It's strongest near the quake's epicenter.
I heard the earthquake coming, so I yelled for Katie to run fast to Mommy. An earthquake was coming. And as I was moving towards her and the open kitchen doorway, this tremendous jolt, it was an explosion that threw me out the door. Katie was trapped inside the house, but luckily not in the living room where the chimney crashed through the floor and the wall and the ceiling and everything. It just stuffed all the furniture through the floor and everything.
As seismic waves spread out from the epicenter of an earthquake, geology becomes increasingly important in controlling ground shaking. Solid bedrock is the most stable material. It's found in the mountains and the hills of the Bay Area. Down in the valleys, it's covered with a material called alluvium. Alluvium is made of rocks and soil eroded down from higher elevations, and it's a lot looser than bedrock. The shakiest type of ground is found where water meets the land, and less obviously, where water used to meet land.
Downtown Santa Cruz responded much more violently to seismic shaking than many areas, to a large degree because it's built on the old floodplain of the San Lorenzo River, which means the river used to meander back and forth through there, such that under the city are thick, loose materials with a high water table, and those kinds of materials tend to respond much more violently to seismic shaking than, say, bedrock areas.
Many of the old unreinforced masonry buildings in Santa Cruz simply couldn't stand the violent shaking of the Loma Prieta quake, and many of them collapsed. Much of the damage that took place around the San Francisco Bay occurred on very loose and permanently wet ground called bay mud, which formed thousands of years ago when the bay was much wider than it is today.
Recording stations on bay mud shook 2 to 3 times as hard as recording stations on adjacent bedrock. The best example of this was the pair of stations on Treasure Island and Yerba Buena, which are in the middle of San Francisco Bay. Yerba Buena is a bedrock outcrop that protrudes up through the bay. Treasure Island is a island built on bay mud, and the recording stations on Treasure Island shook about 3 times as strong as the recording station on Yerba Buena Island.
San Francisco Bay was once lined with marshes up to a mile wide in places, but more than 3/4 of these lands have been drained and filled for development. Ground shaking during earthquakes can be especially intense in these areas if the artificial fills were not engineered for earthquakes. A tragic example of this occurred during the Loma Prieta quake in San Francisco's Marina District, where the ground shook several times harder in artificially filled areas compared to bedrock sites just a few blocks away. This triggered another major geologic effect of earthquakes in the Marina District: liquefaction. Liquefaction takes place when wet, sandy ground is shaken hard during an earthquake. The weak bonds between sand grains are easily broken by the shaking, and the ground is transformed into a watery slurry that has very little internal strength. Buildings and roads on the surface can crack or buckle as the ground shifts, and underground gas mains and water lines can burst. As liquefaction continues, pressure within the trapped slurry may force it to shoot to the surface like a mini volcanic eruption. These are simply called sand volcanoes, and during the Loma Prieta quake, they erupted in artificially filled ground at many sites around the Bay Area. But liquefaction is not limited to artificial fills.
Liquefaction was widespread in young, natural river deposits in both Santa Cruz and Monterey counties. In fact, one sand volcano located in a strawberry field near Watsonville built a mound of sand 30 feet in diameter. Moss Landing Marine Lab, built on beach deposits near Elkhorn Slough, was extensively damaged by liquefaction to the point of being totally destroyed.
The third major type of ground behavior triggered by earthquakes in the Bay Area is landslides. Up in the hills and in the mountains, the Loma Prieta quake caused thousands of slides over an area of 5,400 square miles, and as far as 80 miles away from the quake's epicenter.
The Loma Prieta earthquake caused a large number of landslides, and many were very disruptive. Luckily, the earthquake happened during a drought year. If the ground were wet, many more landslides would have occurred, and they would have caused much heavier damage.
Landslides don't always send tons of earth down mountainsides. It's not obvious, but this neighborhood is built on a gigantic old slide that may have slumped slightly during the Loma Prieta quake, causing heavy damage in the area. But cracks like these must be carefully studied to determine if they are in fact landslide features, or if they represent the fourth major type of ground behavior caused by earthquakes: ground rupturing.
It all happened so fast. I mean, it takes longer to explain it, but it happened so fast. That crack opened up about 3 feet, and a lot of my tools and everything else flushed. They all bounced right into it. It's like everything was headed right towards that crack. The center of vibration was pushing all towards that crack. And then it shut back up. It shut back to about 1.5 to 2 foot.
John Godsey lost his tools during the Loma Prieta quake because his property was located directly on top of the San Andreas Fault. During the earthquake, the land on the west side of the fault was wrenched 6.2 feet to the north and 4.3 feet upward. The actual fault rupture never made it to the surface of the Earth, but the ground was torn and ripped open in a 25-mile-long zone along the San Andreas. Scientists also found ground ruptures that were not near the San Andreas Fault. In a zone running from Los Gatos to Palo Alto, sidewalks, curbs, and roads were buckled as if squeezed together. Los Gatos was hard hit during the quake, and it may be because there are other faults in this area that were jolted into action by the main shock on the San Andreas. The Loma Prieta earthquake showed us excellent examples of 4 main types of ground behavior caused by large earthquakes. And many of these same effects happened in the same areas during the 1906 earthquake, except that the 1906 quake was 30 times bigger and caused much more damage. In other words, large earthquakes in the Bay Area tend to have the same effects in many areas, and these effects can be and have been predicted.
There are numerous reports and maps that forecast earthquakes and predict their effects. The recent Loma Prieta earthquake has confirmed the accuracy of those reports and maps. The information has been collected under various research and monitoring programs.
The Central California Seismic Network, established in 1967, is one such monitoring system. Extremely sensitive instruments called seismometers record nearly every vibration of the Earth's crust at hundreds of sites in the state. Signals from these seismometers are sent by phone line, radio, and microwave to the USGS in Menlo Park, where they are recorded and processed every second of every day. Other types of instruments like accelerographs are installed on buildings, bridges, and other structures to monitor the effects of the earthquake shaking on man-made structures. The Transamerica building in downtown San Francisco is equipped with accelerographs at several different heights above street level. And every strong earthquake brings crucial new data to building engineers. Some of the monitoring equipment must be taken into the field by scientists. This instrument receives radio signals from orbiting satellites so that movement of the Earth along faults can be detected within fractions of an inch. This system was used to determine how far the Earth shifted during the Loma Prieta earthquake. Less sophisticated instruments are used to collect rock samples, which are taken back to the lab and analyzed for a variety of earthquake-related properties. Scientists are getting a good handle on why earthquakes happen and what happens to the ground when they do happen. But can the time and place of an earthquake actually be known before it happens?
At this time, the most useful way to predict earthquakes is to estimate the likelihood of a major earthquake occurring on a fault segment over the next 30 years. The historic record, as well as the geologic evidence for prehistoric earthquakes, are important in these estimates. We also use the average rate of slip on the fault segment in estimating the earthquake probability.
The 2 crustal plates that meet at the San Andreas Fault are slipping by each other at an overall rate of 2 inches a year. But this movement isn't steady everywhere along the 800-mile-long fault. Some sections stick for a long time until they're finally forced to break by the relentless march of the Earth's crust. The section of the San Andreas Fault that broke during the Loma Prieta quake had been locked since the 1906 earthquake, and an obvious blank spot formed in the long-term earthquake record along the fault. By 2 weeks after the main shock, the gap was filled by thousands of aftershocks. Now look further north on the earthquake record. Notice the blank spot along the peninsula segment of the fault. This section broke during the 1906 earthquake, and has been relatively quiet ever since then. On the east side of the bay, the Hayward Fault produced 2 major earthquakes of about magnitude 7 in the mid-1800s. The Hayward has not been broken since then.
When we consider all the major faults in the Bay Area, there appears to be about a 67% chance, or about 2 chances in 3, of another magnitude 7 in the next 30 years. And that event could happen anytime, starting today.
If we have an earthquake today, It most likely will be on the Hayward Fault, which runs from Point Pinole down through Fremont in the East Bay. It won't be like Loma Prieta. Loma Prieta, the people that were at greatest risk numbered about 200,000. A Hayward quake would impact 3 million people. The fault trace runs directly under major urban development in the East Bay, under Berkeley's Memorial Stadium, through the city of Oakland, through the downtown of the city of Hayward, through the downtown of the city of Fremont. We have many facilities such as emergency operations centers, hospitals, schools, very close to the fault. If we have that quake today, it'll be a catastrophic disaster because we're not ready for it.
To soften the blow of the looming disaster, many Bay Area communities are looking at the ground they live on as they draw up their development plans. San Mateo County, for instance, recently had a detailed set of maps made that show the main effects of a major earthquake on every parcel of land in the county. Despite the progress being made in land use planning, it's safe to say that many older structures will be destroyed in future Bay Area earthquakes, and many people will lose their lives if an earthquake strikes with no warning. That reality is a powerful driving force behind the Parkfield earthquake prediction experiment.
I'll be rolling for Froelich here in just a couple.
That sounds good, Unit 1.
Parkfield is a tiny, isolated town in central California, but its rural appearance is deceiving. The surrounding countryside is dotted with the largest collection of earthquake monitoring instruments in the world. The instruments crisscross a section of the San Andreas Fault that has a habit of producing a magnitude 6 earthquake every 21 to 22 years.
The next magnitude 6 earthquake should happen at Parkfield before 1993. So we've installed hundreds of earthquake monitoring instruments to try to record the geologic processes that should happen before the earthquake. We'll also get a very detailed look at what happens during and after the earthquake as well.
The newest experiment at Parkfield is being run by Anthony Fraser Smith, a physicist at Stanford University.
That wouldn't be such a bad idea.
Dr. Fraser Smith and his associates recorded a strong increase in low-frequency radio waves several hours before the Loma Prieta earthquake struck. Scientists are eagerly waiting for the next earthquake to rattle Parkfield because they know that their experiments could lead to a short-term prediction system in heavily populated areas like the San Francisco Bay Area. Many lives will be saved if a reliable prediction system can be developed. But even if short-term earthquake prediction eventually becomes routine, it won't save weak buildings built on shaky ground. And it can't keep weak structures and roads from slipping down hills in landslide-prone areas. These problems have to be addressed years in advance of the big one. What's nice to know is that we've learned how to do that. And since we know that another big one is definitely coming, wouldn't it be nice to know that we did all that we could to ride it out safely? After all, if you love the Bay Area, if you love this rugged, colorful, unique corner of the earth, then you have to respect its earthquakes.